Okay, hopefully this sounds a little bit better. Here we have, this is another presentation, I guess, lecture on our logic topic in chapter 3, section 3. And we're going to be, or rather, I'm going to try to explain to you the rules, or how we apply the rules for conjunctions and disjunctions with regards to the formal evaluation of logic. Typically, we look at conjunctions and disjunctions every day, common sense wise, because when somebody says that they did both things, then both things have to be true in order for the conjunction to be true. When you have a choice, like either or, and this is considered a disjunction, then either one can be true for the entire statement to be true. Okay? So, here we have our title, our objectives for this section, and our first example of where we are looking at what happens to the truth values for a statement. Here we have the truth value for P as T and F, and when we negate P, it'll be the original T and F's become the opposites of each other, F then T. Now, if you notice for the conjunction in its symbolic form, there's an arrow pointing upward. Okay? This is our typical standard notation for conjunction. And remember when I said on the first slide that both statements have to be true in order for the conjunction to be true. And there's a kind of like a mnemonic or rhyme that you can use. I got this from another instructor who teaches this course. And she would say, true and true is true, all else is false. True and true is true, all else is false. So, as you can see, both statements are true for the first row, so therefore the conjunction is true. When either one are false, then the conjunction is false. For the disjunction, either one can be true, or rather, at least one of the statements have to be true for the disjunction to be true. And as you can see, there are more truthfulness when you have a choice as opposed to when you don't. Now, even though our textbook does not identify this, at times you may see, as you may look online or talk to other people, that when there be times where both statements cannot be true, and that's called mutually exclusive, meaning both statements cannot be true. And usually we notate that with a line underneath the arrow that's pointing down. Okay? So unless you see that line, you can assume that both statements can be true. It is like going to Walmart and buying something, two things that are on sale that may be in the same area, and the salesperson may say, well, you can't buy both, or you can buy both and still get the discount. Okay? So, it's that type of thing. Here we have an example of two statements and how they work as in the form of a conjunction. And then we negate one of the statements and see what its truth value is. So in part A, both statements are true, so the conjunction is true. When we negate or make one of these statements false, then the entire conjunction is false. Now, for the same two statements, when using the disjunction or inclusive disjunction, both statements are true, so therefore the disjunction is true. When we negate it, and in this case we didn't even have to negate well, they want to show you how we get to be a false disjunction. And the way we have to is that both statements have to be false for the disjunction to be totally false. Here we have another example where we're given basically a step-by-step process of how to create and fill in the truth tables. Now, you may see, I think on the worked out problems, you might have seen that for columns P and Q, I created two separate columns for them. It doesn't matter, you can put them all in one column or separate columns. But this compound statement, or the statement that you're working with, in its totality, is usually in a column by itself. Okay? So you look to the left, look at those truth values, apply the rule, and fill in the cells below. So since T and T is true, the conjunction and is true. And you go through and fill in false, 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 false. And then, since what we're really looking for is the negation of all of this, the slide would show us another column where we see that we have negating. We're going to negate, meaning change the original truth values for P and Q, the statement for P and Q, and then become where P and Q was true, and now it's false, and you see more truths than falses than we did previously. Okay, so now here's another example of us constructing a truth table, or rather the author constructing a truth table for us. And he has went ahead and separated the way he wanted to set it up. And either way, you can set this up however you want to for the negation parts of the truth table. The reason why he has the not P over here is because when you consider the truth value, it's just easier to somewhat read the two items that you're looking for in the parentheses. And really, to some degree, you should put maybe the not P in between, so that way you could easily read from left to right. But basically, we're only considering what's in this red oval for the parentheses to get the truth values for not P or Q. Okay, so then we get that truth value, and then we consider the conjunction between the truth value for not P or Q and not Q again. And since it's conjunction, both parts have to be true in order for the entire conjunction to be true. Okay, here we have a table showing us, the number of truth value combinations. And usually, what happens is that we only have two results, or two possibilities, which is true or false. But if we raise the number 2 to a power, meaning, like say 2 to the n, where n represents the number of statements. If you have 3 statements, then it's 2 to the third, which equals 8. That means you have 8 combinations. Here we have another example where we're asked to construct a truth value table. And since we're only looking for when T is true, Q is false, and P is true, then the resultant disjunction is true. Okay? I'm going to give yourself a minute to look at this. here, when we're trying to find a specific case of a truth value, we can, and we just replace the statements with T or F and then work out the rules. Here we have two pie charts related to undergraduate freshmen, undergraduate classmen, and one is the number of students in percentage of students, and the other is their death tolls according to the classifications. So now we're trying to find the truth value for this statement. It is not true that freshmen make up 24% of the undergraduate college and account for more than 1/3 of the undergraduate deaths, or seniors do not account for 30% of the undergraduate deaths. And if you go through and look at the original statements, P is true, Q is true, but R is, when you put this together and substitute their values in and start working it out, you get down to be true just because of the breakdown. Okay.